And I commend you for sitting through 2 of these, by the way. I've been looking forward to give this talk for ages. I've been really wanting to give the advanced async talk, but whenever I've done it in the past, whenever I've gone to conferences, people have told me, oh, we've only got 1 slot for you. So I've always been stuck to the basic things. This is my first time at actually... What I wanted to share with you was the async design patterns that we inside Microsoft have developed from the past 2 years' experience of using async. Best patterns, best practices, recommended patterns, exciting patterns. The first third of the talk will be very heavily code, focused on those design patterns based on what we've learned. Middle chunk of the talk will be about the real world. It will be about, you've got a legacy application, and there are lots of comments throughout it saying, warning, do not alter this code. It's probably synchronous up there, and now you're adding a new bit here, and you're using a new library, and you want it to be async, and you're wondering, well, how do I tie into the stuff? Or just how do I integrate async into my existing world? Maybe synchronous or maybe event-based. Final third of the talk is slides only, and it will be about the details of the code generation. It will be about as much of the code generation as I thought was important for you to understand some principles behind it, particularly around performance and how to think about that. And in the third talk, I'll be going on to the ASP side of things. The rest of it's universal. Just before I started, I wanted to share this way of looking at it. Looking at await versus callback, event-based programming style. Pointer options. On the left is how we'd write it using await things. On the right is how we'd write it using callbacks, I suppose. What to notice about it is that this semicolon operator, probably you don't even think about it as an operator, but it is an operator in the language. It's the operator for sequential composition. Doesn't exist in the callback world. So callbacks do not even work with this tiniest operator in the language. How about if statements? If B, then await statement 1A, else await statement 1B, and then await statement 2. If we tried to write this using callbacks, it would be if B, do statement 1A, followed by a callback to statement 2, otherwise 1B, with a callback to statement 2. Basically, we've had to duplicate statement 2. So callback style does not compose with if blocks. How about a while loop? I'm sorry, that's a hideous pink. It looks clearly better on my screen. Anyway, for each with an await inside it, that's fairly nice. How on earth would you write a for each loop using callbacks? Answer, you can't do a for each. I'm not actually even sure that this code is correct. The reason is that it's a using clause here, but we should end the using after all of our statement ones have been completed, rather than just the first one has been completed, and I don't think it's got it right. Oh well. I mean, the message is very clear, that we're in the world, we've left the world of callback programming because it's a bad, bad world to be in. Anyway, design patterns. This slide just summarizes all of them. Once again, all of this talk and all of the code in it will be on my website in a week or so you don't need to write anything. I'm just going to go straight to code, and let's see where we go with that. Then I'll return to the slide, and we'll see what we've done. I started with the WPF application this time. Once again, pretty simple. And I'm sorry for doing such simplistic examples all the time. I really wanted to have complete working code. This one is calling await load picks. And load picks follows the task async pattern. It's got the async modifier. It returns a task. Actually, I should have called it async, shouldn't I? That's part of the pattern. What it's doing is getting the path to the My Pictures folder. It's going to accumulate all of the results. It's enumerating all of the files, the JPEGs in that folder, and then it's loading them, calling a helper function that I wrote, load bitmap async, add it into my results, and it's updating the UI just as feedback so I can see that it's running. And then I stuck this await task.delay just so that the user interface didn't get overwhelmed and bogged down in this work. And if I run it, pretty straightforward. I hit the load pics button, and it goes through a bunch of holiday snapshots. Okay, let's do something with it. We already talked about cancellation. That's pretty easy. Let's just add that. Var cts equals new cancellation token source, and button2.click plus equals once again on the inner loop. It will throw the exception if it's been requested. And once again, I should wrap this in a try block to protect against cancellation. What I've done here, just to keep the code small and local, is I signed up the cancel handler right inside my code. What's ugly is that here there isn't a good separation of concerns. The function that does load pics async is also updating the UI. I would love for this just to be the function that loads the pictures and somewhere else in my code updates the UI accordingly. It could have been with a data-bound list. That would be a natural WPF way to do it. But I'm going to show you another way, which is more general and works arbitrarily in the task asynchronous pattern. Let's start by writing a delegate which will listen for progress. I've created this progress object using the new progress type, and I put a delegate inside it. My idea is that whenever the method wants to report that it's made some progress, then I will hook up my progress handler to it. Let's pass it to it. It's a standard part of the task asynchronous pattern that if you wish to support cancellation, you stick it as the last parameter. If you want to support progress, stick it as the second last parameter. Or use optional parameters if you want. Now, instead of modifying the UI directly inside my logic, I'm going to say if progress doesn't equal null, progress.report of BMP. That's the best way to do progress. Now, if I run it, I hit load pics, and it's updating the UI from the correct place in my code. It's updating it from the button handler rather than the logic. There's something interesting about this way of doing it, using the progress concrete type and the iProgress interface, is that this progress type will automatically marshal things from wherever it was into the appropriate synchronization context. That's not important in this case because we're running this method load picks async on the UI thread. But if we're running it on a background thread, or if it was anything like that, the reported progress, it would automatically get progress back in the correct place. The next thing I want to talk about, okay, so that's number one item. Progress is part of the task asynchronous pattern. Next thing I want to talk about, this await task.delay of 1000, I said for UI responsiveness. Why is that? Well, let's try seeing what happens if it's not there. I do load pics. And my application is just frozen solid. Why is that? It's frozen solid, even though I've got await in here. Ah, finally, it did something. It froze solid because my work was actually chiefly CPU bound. The bitmap loader I had saw that it was trying to load a file from disk, and so it chose to do it synchronously because it knew it could do it quickly rather than asynchronously, and so it finished immediately. And because this loop was just running so tight, the user interface thread almost never got a chance to do anything with itself, never got a chance to update. This is the old familiar problem. And you might be thinking, damn it, has await not helped me at all? Well, it looks like it hasn't. So what are we going to do about this? The task.delay of 1 second was a bit of a goofy way to get around it because it slowed everything down. What we'd really like to do is run as quickly as possible without interfering with UI responsiveness. So let's put await task.yield and run it. Oops. Hasn't helped at all. I led you down the wrong path. Task.yield is a bad API. We thought it was a good idea when we were creating it, but suddenly the release candidate of Visual Studio closed down, and we realized it's a bad API. It doesn't fulfill the commonest need people have of it. We couldn't remove it because we just can't remove things at this late stage in the game. But we did the next best thing, which is add a more useful... Okay, I'm sorry. Ah, because you're down there, you can only see... Okay, gotcha. We did the next best thing. Await dispatch.yield. Actually, I can tell you why it doesn't work, and it should have been obvious to us just at the first point. When we say, I wish to yield control to the UI thread, intrinsic in that is a notion that we wish to yield to things more important than us. And task.yield doesn't have a parameter to say what things are more important than us. Therefore, it's technically impossible for it to do what we want it to do. And indeed, there's no cross-framework notion of levels of importance. I mean, there's something in WPF, and I'm going to use that, dispatch.yield of dispatcher priority.idle. What that says is that, why didn't that work? Application idle. What that says is that everything that's more important, including the UI, including redrawing it, should happen before I get back from this yield statement. I wish to yield at the priority level of application idle. And if I run it this time, then it updates more quickly and it's showing all of the things correctly and it lets me drag better. Let's close that. I just wanted to do something on cancel. Image1.source equals null. What I've shown you here is the WPF way that you can yield control in a busy loop to let the UI regain some chance. Question, what are the other ways, good ways to do it? What is a good way to yield in WinForms or Metro in Win8? For that, please read Stephen Taub's blog. He's been writing posts on this topic and he has the better answers. There's still something pretty ugly about this code, you know. What's ugly about it is that dispatcher.yield is totally part of my UI layer. It's not part of the logic layer, and yet it's inside my logic function. So the question is, how can we promote this to outside it? And I'm going to show you a beautiful pattern that we've been using from time to time. Let's delete all of this. Delete all of this. And start from scratch. Interface, async enumerator of T. Task of bool, move next async, and T current get. If you've looked at the regular .NET enumerator interface, this is almost the same, except the regular enumerator just has a bool returning synchronous move next method. I wanted to generalize it to an asynchronous move next method. And of course that makes sense. I mean, imagine you're enumerating through rows in a database. You're probably going to cache them. You've got 100 rows at a time. Each time you call move next, it might return immediately if it's already in the cache, but if it has to fetch the next batch of 100 rows, then it might take a long time. So it's the move next method that will take time before it can give you the answer of whether there is or there is not more data. Well, how are we going to use that? We're going to create a method. In fact, let's put it down here. Async enumerator of bitmap image enumerator equals load pix async 2. And then I'll implement it. Actually, I won't do it yet. I've got the enumerator while await n.moveNext async image1.source equals n.current await dispatcher.yield of dispatcher Okay, that's pretty good. What we've got here is a pattern where all of the UI layer happens in the UI, where the UI can control the rate at which it asks for more data. If the UI isn't ready for more data, it won't ask for more data. And the function loadPix async2 can also control the rate at which it sends data. If it has nothing available, then it won't give anything. I think this is a beautiful pattern. Do you know what it looks like? It looks like a stream. What is a stream? A stream is something where it's got a fixed buffer, maybe 1K or so, and the producer can put stuff into the stream, but he might block if it's full. And the consumer might take things out of it, but he might block if it's empty. So we've basically implemented what is, conceptually, a stream. Well, except we haven't implemented it. Throws not implemented exception. View toolbox. Here's one I implemented earlier. This is the time when I wish I had a code monkey to help me with it. Okay, I knew that I wished to return some object that implements the async enumerator interface, and I just had to throw it together. And it's not conceptually difficult what we'll do, so I'm not going to spend more time on it than is justified. All that my function loadPix async does is it constructs an instance of this object, loadPix enumerator, that I created for this purpose, and I pass it the relevant information, a cancellation token, and the enumerator over the list of files in the directory. And then as for the implementation of the loadPix enumerator, it has this method moveNextAsync, which says, If cancellation has been requested, I'm just going to return false. I'm not going to continue doing anything. If, also, there are no more files in the directory, then I'm going to return false. Otherwise, I'm going to load the current file name as a bitmap into this current thing and return true, indicating that there is data, so that when someone comes to fetch the current property, they'll find what they were after. Some of you might have seen iAsync enumerator already. That's because it was shipped as part of the RX framework, the reactive extensions, and they use it extensively. And this is exactly the same thing. Wouldn't it be beautiful, though, if instead of doing, where are we? Inside the button click handler, we do this while await. Wouldn't it be beautiful if we could do for each await var pick in load picks async 2? It would be great if we had some async version of the for each loop, which called the move next async rather than the regular one. Unfortunately, we don't have it. Why don't we have it? Partly it was quite difficult to implement and it would take us extra time. But more generally, it would have made this pattern a bit too easy. I'm quite serious about this because what we're writing here is a whole bunch of code that is creating an entire object. It's got a load of state. It has move next async. It's a very chatty interface. Imagine if we did use this for database rows, and imagine if we got batches of 1,000 at a time, and imagine if you invoked this async move next function for every one of those 1,000 rows. Most of the time, the async function would return immediately, and you'd be incurring the overhead cost of an async method without much benefit. You might be misled into using this pattern too frequently and having a chatty interface that winds up being inefficient. What we've ended up with is it's not too difficult to use, and it's very clear what you're doing, and you're clear that you're using it frequently, and you're clear about the chattiness, and that's just the roadblock, the speed bump to make you stop and think. That said, I was on the side that wanted it to get into the language. Let's try something else. We had some questions after the last talk about void returning asyncs. And one of the loudest complaints we've had is, why do you have void returning asyncs? Because they're dangerous, basically. All of the code that you write, apart from the top level event handlers, should be returning task or task of t. It should not be returning void. But then people ask, well, I wish to launch something in a fire and forget manner. In fact, let's do some of it. Let's, up here, let's await for some computational work to happen, and I'll get it out of the toolbox. No, I won't. I'll generate it from source. And I'll get it out of the toolbox. I've got a really stupid fire and forget task that I want to run here. All it does is change the label content, then it invokes a helper function to download a bunch of data, then it uses task.run with a compute fast Fourier transform function that runs it on the thread pool so as not to interfere with UI responsiveness, and then it updates the UI and says, hey, I've finished with the fast Fourier transform. And I run it. It shows the ... Once it's finished, it says finished FFT, and it gets on with the regular work. But I think to myself, wait, that doesn't make sense. I would like it to do the work in the background. I don't want to wait for it right here and now. I just want to leave it running. One way I might do that is delete the await word. Well, that will certainly start it running, and it won't wait for it to finish. A warning pops up. It says, warning, I'm sorry, I didn't increase the font size. It says, warning, because this call is not awaited, execution of the current method continues before the call is completed. Consider applying the await operator to your call. You think to yourself, well, I didn't want to apply the await operator. I just wanted to let it run in the background. Let's do it properly. Let's say task T equals do work async, and then at the end of the method, I can await T. It's a really good pattern. Whenever you launch something async, just await for it at the right time. Maybe later, maybe like I was using this outstanding list of tasks, but wait for it somewhere. How about if I really thought I was being smart and I didn't want to do that, and I didn't do this, the warning message just says, warning, it returns a task, but you're not awaiting it. So I thought, I can make this a void returning async. Question, what will happen in this case if an exception is thrown somewhere? Where does the exception get thrown from a void returning async method? It can't be thrown back to the caller because the caller has already executed this statement. It's probably executed the rest. It might well have left the entire message. The answer is, if you have a void returning async method with an unhandled exception, then the exception would be propagated to the calling synchronization context. It will pop up to the UI thread in this case. That's really bad programming. You know, it's bad to have exceptions being unhandled, throwing up to the top. The only way I can imagine this being legitimate, let me say that again. The only time I think it is legitimate to have a void returning async is either if you're at the top level event handler, or it's normal for top level event handlers if they have unhandled exceptions to throw them up to the UI, or if your void returning method never catches any exceptions. But then you think, wait a minute, he's just written a catch-all exception. That's bad practice. Yeah, it is bad practice. So you shouldn't really be doing it. You should always be awaiting, either directly or indirectly, all asynchronous things you do because of this danger of exceptions. Or, if you really want to do it, let's try another way around it. Have it return task. Having it always return task is a good thing because it means that if one user wants to launch it in a fire and forget method, they can, but if another user wants to wait till it's finished, then they can. So returning task gives the maximum flexibility. The recommendation is var dummy equals. I saved it into a dummy variable just to get the compiler to shut up with its warning. That's not good practice. The person reading my code says, why did you do this? So, note, I used dummy because I guarantee that do work async throws no exceptions, and I want to launch it fire and forget. Our recommendation is, if you're using this trick of assigning to a dummy to silence the warning, always put an explanation somewhere in your code. Or, if you want to just do it more generally, you could make an extension method, let's say, fire and forget. Something like that. Some clear indication to the user that you know what you're doing and that this is safe, and be aware of adding any exceptions to the method. That's our recommendation on that part. Let me give you another recommendation. Look at this routine. await task.run of delegate of library.compute_fft. At this point, the guy who wrote the compute_fft library function is thinking, what a pain. My consumers are probably all going to be using task.run, so why don't I offer them a task.run async version of my compute-bound work? Let's see what that would look like. I've already got the compute_fft function. If you look at it carefully, you might notice that it doesn't compute the FFT. But let's just pretend for argument's sake. Return task.run of task.run of Okay, what this library author has done is he's offered an async version of his API that is merely a wrapper that creates a thread around the synchronous version of his API. Seems reasonable enough. And the user can change their code to no longer do this. They can just do await library.compute_fft async. This is bad practice. Why is it bad practice? Because we should be in the business of telling clients of our library the truth. If something is compute-bound, then we should give them a compute-bound function. It's up to the user of our library to decide how many threads he wants to allocate. If he's on ASP, he won't want to allocate any threads, because that would be a complete stupid thing to do. If he's a top-level event handler, then yeah, he will choose to create threads. Creating threads is such a heavyweight operation that it should never be done implicitly. So the guidance there is never create this kind of wrapper around your APIs. Let's see what I've covered so far. I talked about the task asynchronous pattern, which we've already seen. I talked about the iProgress type and how we use new progress of T and it always comes back on the user thread. I talked about task.yield, which doesn't. I talked about the async enumerable pattern, which is a beautiful pattern where it's appropriate, where it's not appropriate if most of the time it will be ready immediately. It is appropriate in other places. I said, don't wrap synchronous APIs as async. And don't wrap them the other way around, actually. If you have an asynchronous API, don't offer up a synchronous version that merely calls the asynchronous version. That's not doing users any service. The user, by looking through IntelliSense, should have a good feeling of which of your methods are safe to call and which are not. And I talked about fire and forget APIs and how dangerous they are, but how they're the only use of void asyncs in certain cases. Let's move on. Integrating async into existing code. I'm going to go back to the code, actually. Let's start from a fresh slate. What should we do? In this case, I imagined that I have an existing application. In this existing application, I'm sorry, again, it's a toy example. It updates the label. It invokes one subroutine synchronously, and then it invokes another routine synchronously. And the chief architect said, warning, do not change this. Or maybe it just said it must be synchronous, because the top level, maybe I'm not in control of it. Maybe I'm only in control of a small corner of the routine. And here I've been asked to implement this subroutine 1, which has to return by the time it's finished. It is not an async method. How am I going to do it? Well, let's have a concrete example to work with. Let's suppose I wanted to helpers.download data async again. It says await. Oh, I need the async modifier, and I need it to return task of int, and I should call it the async version. But then the caller has to change into await, and then the caller needs to put async. But I was told, warning, should not change this. I have to figure out a different way to put an await corner into my existing piece of code. Let's factor it out. Task T. What if we did t.wait and then return t.result? What's that complaining about? Interarray. Is this going to work? Heck no. We know from the message pump diagram that we've mixed synchronous and asynchronous in the same program, and it's going to lead to the deadlock. We can't do it that way. We'll have to do it a different way. Oops. Well, here's one I did earlier again. You know how when you do message box.show, then this is kind of a synchronous routine in that execution doesn't return until after it's finished, but it still manages to pump messages just fine with a nested message pump. That is the only way, basically, that we can integrate our corner of async into an existing synchronous application. And I wrote one that does that, t.wait with nested message loop. If I run this, loaded. Okay, so it's working okay. I didn't show you that it was responsive in that time, but it is. I used a nested message loop here. Hopefully all of you at this stage think, oh my God, no, nested message loops are terrible. It's true, they're terrible, but they're the only thing we can do in this case. Let's look at how I implemented it. It's not how I implemented it, it's how I went to Stephen Taub's blog, copied down what he had written and put it into my code. He's written a lot more about this. Wait with nested message loop. The sole reason for this routine is to block until a task is finished. If I were doing WinForms, it would be easy. I could just do this loop. While the task is not yet completed, application.doEvents. Kind of a busy loop, actually. WPF is, of course, better architected and, of course, much more complicated to understand. But this code does exactly the same thing. It creates a nested message loop to accomplish exactly what we wanted. That's the one side of putting an asynchronous corner into a synchronous existing body of code. What about the reverse of putting a synchronous piece of code into an asynchronous harness? You know that we don't want to run the synchronous, in other words, the blocking code on the UI thread. So we're going to create task.run to run it on a background thread, exactly as we saw already with this compute FFT routine. How about if we're up here? Okay, I'm going to write something different. button1.content equals ready. I'm going to have, like in Top Gun, he wants to launch the missiles, but he can't just press the button, he has to flip the cap. first and then the button is exposed. I'm going to do the same kind of thing here using await in a surprising way for the control flow. So when you hit, the button normally says ready, but when you hit the button, it's going to uncover it and say fire. The question I'm asking is, how can I integrate an existing legacy functionality like the button click handler with new functionality like async? Here's my idea. In other words, how can I turn an event-based thing into a task-based thing? Let's write the code for it. So what this guy did was await button click of button 1. In other words, button click had to return a task, or at least something awaitable. The first thing it does is var TCS equals new task completion source. What is a task? A task, remember I said in the olden days, a task, people used to think it meant a background thread pool item that run on the thread pool. That's not true. A task is merely a promise. In other words, a task is an object which exists in one of 3 states. I haven't yet completed, or I have completed successfully, or I have completed with an error. Various events can cause it to transition from the first state to one of the other 2 states, but that's all it is. It's an object with states that you can hang off continuations that get fired when it transitions to one of the states. So I'm using TCS as my factory to create one of these tasks, one of these promise objects. I'm going to sign up a button click event handler. OnClick is a delegate which says as soon as it's fired, I'm going to unsubscribe from the button click handler, and then TCS.setResult. I'm going to transition the object from its not yet completed state into its completed state. Question, why am I using task completion source of object? I'll just say, and then of course I sign up the button click handler, and then it returns TCS.task. TCS.task is a task of object. My method was only supposed to return a task. Why didn't I just use var TCS equals new task completion source? Use the non-generic form. Answer, the non-generic form doesn't exist. Just, there didn't seem any point adding it to the framework. So we use the generic form, and that's fine because task of T inherits from T. Anyway, write this code, run this code. It says ready, hit the button once, it says fire, hit it a second time, and it executes. This is a silly example, honestly, and it's not quite good because the button click handler at this stage has 2 handlers, this one and this one, which are both active, and so I really wouldn't write this. The important thing I wanted to show you was only this routine. This is the core of every time you're going to turn event-based things into task-based things, and there are a heck of a lot of them. One example I had, in the demo I did in the previous thing, I had a storyboard. I wanted to await until the storyboard had finished. When a storyboard finishes, it fires an event. But I want to await until something is finished, so I needed some way to turn the storyboard event into a task. I did it exactly using this style. Let me give you another example. I had a bitmap image. You know how in WPF or Windows 8, when you create a new bitmap image from the source of a URI, it loads it lazily, it loads it asynchronously. You've got the bitmap image, which says, I will come from this URL, but it does not yet load it from that URL until a bitmap image is put there on the XAML, on the form, for it to be displayed. I wanted to write await until the bitmap image has been loaded. The reason I wanted to do that is because its pixel width and its pixel height property are not valid until after it's been loaded. And what if I wanted to base its position on the form based on its pixel height? Then I really need to await. I used exactly the same thing. If you have a bitmap image, then it has events for successfully loaded and for failed to download properly. And so I needed to actually add two delegates. I needed to add onClick success and onClick failed. And in the onClick failed, it invoked tcs.setException with the exception thing. Anyway, this was a completely general mechanism for turning your legacy events into tasks so you can use the task asynchronous pattern. And there's one other neat thing we can do. Let's suppose I wanted to be flashy. If I want to just await this guy. Maybe I might not want to do this, but you can imagine doing await storyboard would be a very fluent way of writing it. There is a way to do it. Task awaiter. I'm going to create an extension method. I thought that was enough. Get a waiter, thank you. Once all of that's present, as long as there's a method called getAwaiter that can be invoked off the thing, either extension or an instance method. I'll put that up so you can see it. If we have that, then you can await the button directly. Oh, I have some stupid bookkeeping to do because, as I told you, it doesn't have the thing, has the non-generic thing. So I just had to put it into the non-generic form. Here we have a technique where you can make your own user-defined types awaitable. That was what I wanted to say about integrating it. I wanted to talk a bit about the code gen and the performance. Is any of this visible at the back? There's complete silence, so maybe it's not even audible at the back. I see a raised thumb. The user writes async task foo async with the body inside it. There's a heck of a lot of stuff here, and I don't want you to pay attention to all of it. And the slides are available offline if you want to look in a week's time. That's when they'll be available. But I want to say that this grey stuff is what the compiler generates. First, the compiler generates a method with exactly the same signature that you had, task foo async. What it does is it creates a new state machine object, blah, 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 and it returns builder is async task method builder. That's exactly like the task completion source that we saw earlier, in fact. It is a way of turning events into tasks. That's what we're doing, and it returns it. And the body of the method has been munged into this private void move next. And I've just put it here. The transformed body goes here. Oh, and you can see here it calling set exception and set result, exactly like task completion source. So, if you're looking at your profile logs and you see, oh God, this awful function move next is stealing all of my CPU cycles, how do I get rid of it? Don't think that. Move next is just the function you yourself wrote. You can also see that there's overhead here. There really is. So don't put async methods gratuitously. If something is not really async. Question, what is the overhead for invoking a method? Let's assume that it's got an empty method body. What is the overhead for merely invoking a method? Well, if it's an async method, the overhead is 3 times what it is for invoking a non-async method. It might seem a lot, but of course, as soon as you put a single statement in there, or 2 statements or 3 statements, it will be dwarfed by it. But that's the ballpark figure to keep in mind. What does it actually look like? Here I've written code which says console.writeLine of A, then it has an await, then console.writeLine of B. So the code that the compiler generates has console.writeLine of A, then it calls this operand of the await dot get awaiter. That's exactly the get awaiter thing that we saw before when we made the button awaitable. If the awaitable thing has already completed, then let's just get the result from it immediately. Get result. The job of this is to return the result or to throw any exceptions if there were exceptions from the awaitable thing. Then it nulls out this temp field. We can't just null it out. We have to assign it because it's a structure type with something, the default value of that type. And the reason we null it out immediately is for garbage collection purposes, so there are no dangling references. This is what we call a hot path. If the awaitable thing had already finished, then it just zooms through here really quickly. But if the awaitable thing had not yet finished, it has to do extra work. It has to save the state where it got through in the method, more assignments, and it calls this builder.await onCompleted. God, this function is so difficult to understand, and I'm not even going to try. All I want to say is that it calls into the awaiter object in some way, and it passes it a delegate, and later on, when the awaiter object is finished, then it invokes that delegate, and that delegate causes execution to resume right here. Well, what I wanted you to take away from this is that if you can get through the hot path quickly, your perf will improve dramatically. Let's talk a bit more about code gen. Here I've got int x equals 10, await t1, int z equals 10, and then inside I've got a nested scope that says int y equals 15. What's it going to do for this? Well, it's going to create the state machine class, and all variables that were in scope at the same level as the await will be lifted into the state machine. All variables that are in a scope that has no awaits will be left local. Actually, that's the statement for C#. For VB, it just lifts everything to the state machine. That's because of some design reasons in the VB language. What this means is that if your method accesses local variables like x or z, the compiler will transform them into field accesses. And field accesses are substantially slower than local variable accesses. My rule of thumb was about 5 times slower. So if you're going to combine an await statement with some CPU-bound work down here, watch out for this. Maybe factor the CPU-bound work into a separate thread. Ooh. I was going to look at the actual IL that gets generated in subtle cases, but it's a bit over the top. Let's review things first. Performance. Measure perf. Figure out what the bottlenecks. We see people thinking, oh, I've got to micro-optimize my async code, but what they don't realize is that 95% of the time is being spent waiting for the network. If you're doing that, there's really no point putting any effort into the CPU-bound stuff. Really, look at your code with a kind of network big O notation view first. If you're doing 2 network loads sequentially, but you could do them in parallel with the task.winAll, that's where you'll get your bigger performance wins than micro-optimizing. Performance. It's very clear that when we're writing a client application, WinForms, WPF, phone, desktop, we're optimizing for responsiveness. But when we're writing server applications for ASP or Azure, we're optimizing for throughput. Here we did some experiments. We made a server. This server makes a query to a back-end service to get an RSS feed. It parses it, and it returns a page with the feed's title. We could implement this in an async way with an async download feed, or we could implement it synchronously with a synchronous download feed. Which is better? You know, if you just think about it, it's not clear, because the synchronous case has the extra overhead of creating of tying up an entire thread, but the asynchronous case has the overhead of creating that asynchronous state machine, and the little overhead I talked about earlier. Also, they go through different code paths in the .NET framework. The async download thing is a different code path from the sync download thing, and up until this release, the async code path was a bit rusty. It hadn't been optimized as hard as it should. In the old days of ASP, you had a thread pool of 20 threads, which means that if you tied up a thread for too long, bang, all of the threads were exhausted and you couldn't handle any more requests. In the modern day of ASP, you have the full thread pool available, and it goes quite well if you configure, if you tweak the things. Say, if you raise the max thread pool up to 1,000 things, then it can deal with as many threads as it will realistically be able to handle. In our experiments, we did get a bit better perf with async. You can see just being able to handle a few higher requests per second. And actually, all commercial web services and things like Node.js have also moved async just because it has the potential to be more efficient, whether or not we've reached that dream yet with the current .NET. Question: if we are using synchronous ASP, does the thread pool ramp up quickly enough? It was another experiment. We start with no requests per second, and then we zoom it up to 750 requests per second. I picked that number because I happen to know, after we'd tweaked ASP's thread pool, that it could, once it built up to enough threads, it could handle that rate pretty well. But look at this. The thread pool climbing algorithm does so pretty slowly. 5 minutes, and it still hadn't responded to the burst in traffic. So, async responds immediately, of course. That's one of the reasons why async was handier. I have to stress, measure perf forms, and only if perf is a problem, then try ideas. Here's one idea. Async task F, return await load async. If I look at a method and it has return await, I'm a bit suspicious. Because remember, the whole point about the async modifier is it wraps up the return operand into a task. And the whole point of the await keyword is that it takes a task and it unwraps it. So this code could more simply be written without an async method. That's good. And we can use this trick in some useful places. Here, I'm going back to the async enumerator. It says, well, my original code used to enter the async method in all cases, but if I already had data, I'd just return it immediately. But what I can say, and then do await if it didn't have data, I can make it into two separate methods for performance. If the data is already available, then return task.fromResult of the thing. Task.fromResult will create a task much more efficiently than the whole async machinery. Indeed, in the simple cases, 0, 1, 2, 3, true, false, empty string, task.fromResult just returns a pre-allocated result, so it doesn't even have any heap allocation. Only if the hot path was not available did I fall into the slow path. So really, I can hand optimize the hot path. What I told you about the lifting variables is that if I've got an await and CPU-bound work in the same method, here buff is used in the await and also inside the CPU-bound work, I should factor that out into a separate thing in my ASP to improve throughput. Finally, if you don't need to return to the UI thread, remember, after an await, it always returns back to the calling synchronization context. If we're inside a library routine and we don't need that, like while we've still got more stuff, await, load more async, I could have just done .configure await of false. That tells it, don't bother returning back to the UI context or wherever you were, just continue with this method wherever you happen to be. That will be quite a lot quicker. The UI threads is a very slow thing to return to. Comparative, I mean, fast by UI standards, but slow by internal computation standards. Those are the performance and optimization things I've got. By the way, for you guys in Redgate, there was one slide that I put in. Oh yeah, this shows what IL is generated in the more complicated cases. And I didn't talk about that at all. And I'm not going to. That's everything I wanted to say. I've given you an idea of the design patterns that we've learned over the past 2 years. This is just a start. The first of those years was spent furiously fixing bugs, trying to teach other people about async, just getting the feature working in the first place. So we haven't had that much of a runway to develop the best practices. And actually, what I'm really hoping is that it'll be you guys who come and figure out the best practices and write blog posts, and then we'll look at what you've written and develop it. I've also shown you the mixing techniques for how to mix async into your legacy code, into event handlers, how to put sync inside a message loop. And with these hints about performance and code gen, I think you have the opportunity to create responsive, high throughput, responsive client apps or high throughput Azure or ASP apps. Thank you very much.